Okay, we've been looking at different series and trying to determine if they diverge or converge. And in 9.5, we're going to look at strictly alternating series. And what we mean by alternating series is simply the series whose terms alternate from positive, negative, positive, negative. And remember that that happens a lot when you have that when you see something like this, a negative 1 to the n minus 1 power or n plus 1 power, or negative 1 to the n power. That means we're going to have that alternating positive 1, negative 1 in front of that. Okay, so the nth term of an alternating series is always in this form. And then what I want you to notice is, as I'm going to be talking about the alternating series test, we have b sub n, and when I say b sub n, that's the absolute value of it, of the whole term a sub n. So I'm ignoring the positive negative part of it. Okay, so our alternating series test says that if we recognize we have an alternating series, then we need to check for two things. First condition is that b sub n plus 1 has to be less than b sub n. So basically, we want the next term to be smaller than the previous term. Okay, so we want the terms to be generally decreasing. All right, remember we're talking about the absolute value of that. The second condition is that if we take the limit of the b sub n term, then we will get that it's equal to 0. So here's just a visual of that happening. So if I start with 0, okay, and then I have my first term, which is b1, so I'm adding b1, so let's say that's a positive b1, so it comes over here, right? So right here. And then if I add the next term would be negative. So that's gonna, if I add that to this original one, then it's gonna take me back here. Now, if this is decreasing, then it won't go all the way back to 0, right? It'll be a shorter distance. So it's gonna be somewhere in here. So now if I add the next term, my b3, that because it's positive, I'm adding it, so it's gonna increase it. But again, it's not gonna increase it by all the way back to here because it's smaller than this distance. So it's gonna end up somewhere in the middle there. So it's going to keep alternating back and forth and getting smaller and smaller and whittling back until we get to some number. So that's why if we have these two conditions, then we know that that series is convergent. Okay, so we're going to come back to this diagram in a little bit. So let's look at some examples to see how we can do this algebraically. All right, example 1. We have the alternating harmonic series. Remember, harmonic series is the 1 over n. So you can see these would be the first few terms of the alternating harmonic series. First one is positive 1, second is negative 1/2, positive 1/3, negative 1/4, and so on. And here's how that term looks, the negative 1 to the n minus 1 over n. Okay, so if you notice, the b sub n plus 1 is always less than b sub n. So for example, 1/4 we know is smaller than 1/3 and so on. And then 1/3 is smaller than 1/2. So we know that that's always true. Algebraically, we can do that by doing this 1 over n plus 1. So you're just plugging in n plus 1 in for n here. Remember, we're ignoring the alternating part. And if I compare that to 1 over n, remember that whatever n happens to be, if I have this this denominator will always be larger in the n plus 1. So if my denominator is larger, then that whole term will obviously be smaller. So this is always true. Okay, and then for the second part of the condition, again, we're looking at just the b sub n as a series. Okay, and this really shouldn't say it's equals 0. We're not saying that the sum is equal to 0. We want to look at the limit here. So we're looking at the limit as n approaches infinity of my b sub n. And remember, we said that the b sub n is simply the 1 over n part. We're ignoring the negative 1 to the n minus 1 power at this point. So if we take the limit of that, obviously if we have infinity in the denominator, that is 0. So we've met both conditions, and you can see that both numerically and algebraically that that's true. So the alternating harmonic series is convergent because it met both of those conditions for our alternating series test. Okay, So what happens if you don't have that? What does that mean? Let's look at this next example, example 2. All right, so here we have this series. It's alternating because it's -1 to the n. And so the 3n over 4n minus 1 is our b sub n. Okay, so I'm going to do something. What I like to do with alternating series is I actually like to try the second condition. I like to do the limit first, and I'll show you why in a minute. So if I check for that second condition, the limit of b sub n, so I'm drawing the limit of 3n over 4n minus 1. And remember, we can divide everything by that highest power in the denominator. All right, and if I do that and plug in infinity, this is going to go to 0. And then I just have 3/4, or you can use that horizontal asymptote rule. So obviously this does not meet that second condition. This should be equal to 0 in order for us to use the alternating series test. Since it's not, we can't use this. Now, just because you can't use this test doesn't mean that it's divergent. Okay, so be very, very careful. It just means you have to use a different test. Now, here's why I like to check this second condition. If this second condition is not met, then what's nice is you can check the nth term test for divergence very easily. Okay, so the nth term test means that we are going to consider the alternating part now. So if I consider this, this is going to be alternating, right? So this is going to go positive, negative, and even if it eventually evens out to 3/4, it's positive, negative. It doesn't actually reach a limit. So this does not exist. It's oscillating, right? So because the nth term is not equal to 0, then we know this is a divergent series. Okay, so yes, it's an alternating series, but we could not use the alternating series test, so we had to use a different test, which we found the nth term test was helpful there. Okay, now let's say you had started with the second condition and it did equal 0. Well, then you do like what we did with the alternating harmonic series. If this is equal to 0, then you go and prove the first condition, and then you can either use the alternating series test or not. Okay, so just remember that just because you cannot use the alternating series test does not automatically mean that it's divergent. Okay, the other thing I want to talk about is the remainder. If we use the alternating series, we can estimate what the partial sum is. Remember, we can't always figure out what the sum of a series is, right? We could only do that for geometric and some telescoping. So we can estimate the sum if we have an alternating series test series. And here's what we say about that. So the error involved with using the partial sum. So we use the partial sum S sub n. This is not equal to the sum. This is an estimate, okay? Okay, it's an approximation of the total sum S. So obviously the remainder, we're going to call that capital R, is simply the actual sum minus the approximation. Makes sense, right? So this theorem says that any series that satisfies the alternating series test, that the size of the error is smaller than b sub n plus 1, which really means that the error is smaller than the absolute value of the first neglected term. Okay, so let's go back. What I wanted to show you is I want to show you with that diagram. All right, so this is our algebraically what we're saying. The difference between the actual and the approximation, the absolute value of that obviously, is going to be equal to the remainder, and that remainder is less than or equal to that first neglected term. So if we go back, and I really want to change this, this should really be not S sub 5, but B sub 5. And this should really be B sub 6. Okay, so what we're going to do is, in that figure that we were looking at before, we're going to look at the difference between the S and the S4, and I want to show you how that it will be less than that first neglected term, B sub 5. So going back, flip back to your diagram here. I'm going to erase all my little blue tick marks. All right, so here we have S. So this is the actual, wherever that happens to be. Notice that I don't have any actual numbers here, but this is the actual sum. That is what the series actually ends up being. Now, if I look at that, and then here's S sub 4, right here. The difference between S and S4. So it's like I was trying to use the first 4 terms to get my approximate sum. Okay, so if I added all those first 4 terms up, this would not actually be the sum. It's an approximation. And the difference between those two, notice that it's less. See that difference there? That's our B5. That's how much we would be adding if we were to go one more term after the 4th term. So notice that this distance has to be less than that distance. Okay, same thing if I did, let's say I did the difference between S and S sub 5. Here's S5. Okay, so if I use 5 terms, okay, it's still not the same as the sum, but that difference has to be less than how much I would be adding in the next term. Okay, so that's all that means with the error. And if you want to, actually, yeah, let's look at on page 633. So go ahead and pause this video and get your books out, and we're going to look on page 633 for the example. All right, so if you look at example 4, all right, this is how we actually use that approximation for the sum of the alternating series. So you have that series alternating 1 over n factorial. Okay, so obviously first we need to check the conditions for the alternating series. Okay, so does the limit as n approaches infinity of 1 over n factorial, is that equal 0? Yes, it does, obviously. Okay, so that first criteria of this, actually it's actually the second condition, but we like to check that first. So then is 1 over n plus 1 factorial, is that always going to be less than or equal to 1 over n factorial? So is it? And not, I'm sorry, this shouldn't be equal to, it's just strictly less than. Okay, and then yes, absolutely, this denominator will always be larger, so yes, that's true. So we have those 2 conditions met. All right, so notice that it says use the first 6 terms to approximate the sum. So if we use the first 6 terms, that's S6. Okay, so the first term is 1, second term is negative 1/2, third term is 1 over 6, fourth term is minus 1 over 24, fifth term 1 over 120, and then the 6th term is minus 1 over 720. All right, so you see how they did that. And all of that is, if I do the decimal approximation, is 0.63194. Okay, so that's our estimation. So the error tells us how close is this, right? So the error says the actual sum, the difference between the actual sum and this sum that we use to approximate that, that's going to be exactly equal to the remainder. And that remainder has to be less than or equal to the first neglected term. So what would have been the next term here after the minus 1,720? That would have been plus 1 over 5040. So 1 over 5040 is approximately equal to 0.0002. Okay, so that's how close we are. So this is going to be plus or minus 0.0002. Okay, so our actual sum is that plus or minus 0.0002. So that's pretty accurate if you think about it. All right, so that's how we use that error. The other thing we need to talk about in this section is absolute and conditional convergence. Okay, so absolute means exactly what you think. We're going to be taking the absolute value of all the terms. So if I have any series, okay, it can be alternating or not alternating, but we can consider the corresponding series of when we take the absolute value of each term. All right, so we call, this is just a classification, a series, we call it absolutely convergent if the absolute value of all the terms, if we take the absolute value of all those terms, then that series is convergent. Okay, and I'll give you some examples in just a minute. And then the series is called conditionally convergent. So think about it. It depends on the condition. So if the original is convergent, but the absolute value is divergent. Okay, so if you take the absolute value of a series and it's convergent, then we call it absolutely convergent. If you take the absolute value of it and it's divergent, well, go back and check the original. If the original is convergent, then we call it conditionally convergent. If it's divergent, then it's just divergent. Okay, so it's just a way to classify a series. All right, so for example, in example 3, we have an alternating series, and it's an alternating series of 1 over n squared. Okay, so this is like our p series. So if I take the absolute value of all of the individual terms, then obviously that is a p-series, and since the p is greater than 1, then we know it's a convergent p-series. Okay, if I look at the alternating one, so if we follow the alternating series test, we know that the limit as n approaches infinity of 1 over n squared, that's going to be equal to 0. And we also know that 1 over n plus 1 squared is going to be less than 1 over n squared. So that makes the alternating series convergent as well. Okay, so the absolute value was convergent and the original was convergent. That means it's absolutely convergent. Okay, and actually what's nice about the absolute convergence is if I know that this series is convergent, we don't really have to do this. If it's absolutely convergent, then the original is also convergent. Okay, so that's pretty nice. So if you have an alternating series and you just want to, and you recognize the absolute value of that as a convergent series, then it's nice, it saves you some work. Okay, however, let's look at example 4. All right, so example 4, we have that alternating harmonic series. So we know that the alternating one is convergent, but we also know that if we take the absolute value of that, that's the harmonic series, and that's divergent. Okay, so what was I going to say? So here's the absolute value part. That's divergent. However, if we do the alternating series test and know that the original is convergent, then we would classify this alternating harmonic series is conditionally convergent. Okay, so practice that, and we will continue with our next lesson.